let's go in and let's take a look at another one of these, linear types of examples. Let's take a look at one like number 27. Okay. So 27 reads, it says, consider the charges in the figure. Find the magnitude and the direction of the net force on charge 2, which is plus 5 microcoulombs, if either A, Q1 and Q3 are plus 5 microcoulombs, or if B, Q1 is plus 5 and Q3 is minus 5 microcoulombs. I'm only going to do one of those, and I'm not super happy with the way they changed the problem from the previous edition, and they made it nice and symmetric. I want to actually take some of the symmetry out of the problem. So what we're going to work on is what is the net force on charge 2. Okay. And they may or may not say that word net in there. And I'm going to alter the diagram slightly so I can get rid of the high degree of symmetry. Okay. And so what we have is that the origin is located here. And this is positions given in meters. This will be the plus x direction. This will be the minus x direction. And so then our charge 1 is at this, 1 meter location. And then we will put charge 2. Let's go ahead and put it at the 4. So 1, 2, 3, 4, 5. And so charge 1 is going to be plus 5 microcoulombs. And then charge 2 is going to also be plus 5 microcoulombs. And then charge 3 is going to be minus 5 microcoulombs. Go. Now again, object of interest is our charge 2. So then what we're going to do is we're going to utilize an idea called the principle of superposition, or a superposition principle. So we're going to calculate the electric force between charge 1 and charge 2 as if charge 3 does not exist. Then we'll calculate the electric force between charges 2 and 3 as if charge 1 doesn't exist. Then we will vector add those two forces that act on charge 2 to get the net force on charge 2. Okay. And so, like I said, this is called the principle of superposition. Then what we can do is we can go in and calculate the magnitude of the electric force on charge 2 by charge 1. So I don't normally do a lot of these extra subscripts. So this is on charge 2. This would be by charge 1 kind of things. But I'll start off with them to begin with, and I'll probably lose them in just a bit. So this is our Coulomb's constant, absolute value of charge 1, absolute value of charge 2, and then that distance between charges 1 and 2 squared. So we're going to come into our diagram, and we're going to note that this is the distance between charges 1 and 2. So this was at 4 meters, this was at 1 meters, and so what we get is this should be our 3 meters. And since we have 3 significant digits in the charge information, then we'll carry 3 digits in the spacing information between those. And so then let's go in and put in our values. So this is our 8.99 times 10 to the 9th. That's the value for K, our Coulomb's constant. Charge 1 would be 5 micro, and charge 2 is also 5 micro. We're going to take the absolute value, but they were positive, so that's fine. And since they're identical, we can just square these. Micro is one of the metric prefixes you need to know offhand. That is 10 to the minus 6. And we're going to square it, or we could write it twice. I'm just going to square it because I'm lazy like that. And then we're going to have our 3 meters squared. Probably the most common mistake is to drop the square in that denominator. And so let's not do that. And then let's evaluate this magnitude of the electric force between charges 1 and 2. Yep, thank you. 2.50, 10 to the minus 2. Now that we have the magnitude, we can go in and work to get the direction between these forces. And so we have, they're both positive charges, so they're going to do what? Are they going to attract or repel? Going to repel. And then they're going to go away from one another like this, but then I only care about the charge on 2. I don't care about the force on charge 1, because charge 2 is our, charge of interest. And so then what we're going to get here is that my electric force on charge 2 by charge 1 is going to go to the right. Now in this coordinate system, to the right is coded as positive, so I could code this as a plus 2.50 10 to the minus 2 newtons. Everybody good? So I have my magnitude, I have the direction, we kind of coded it in the coordinate system. So we're in pretty good shape. Now let's do the force between charges 2 and 3, as if charge 1 doesn't exist. So on 2 by 3. And so from our diagram, we see that the distance between charges 2 and 3 is just going to be this, 1 meter. Okay, because this was at 5 and this was at 4. So the difference is just 1. And if we put in our values, then we're going to get the same kind of thing. So 8.99 times 10 to the 9th. Charge 1 is plus 5 micro. Charge 3 was minus 5 micro, but we're going to do absolute values, so they're identical. Our 5 times 10 to the minus 6. And so I can square that divided by our 1 meter squared. And so then really the only thing that changed between the first calculation and the second calculation is that this 3 becomes a 1. You want to watch out for your square here. And if you have like a second entry option on your calculator, you can go back up, pull it down, and change the 3 to a 1, and it goes pretty quick. And Saeed has it. It's 2.25 times 10 to the negative 1. Newtons, like so. And so now we can worry about the direction. So now notice that when we look at charges 2 and 3, they have a positive and a negative, so they are oppositely charged. And so then they're going to do what? Are they going to attract or repel? Good, good, good. William agrees. Like we had previously with Saeed and William. Yeah, so they're going to attract towards one another, but then I only care about charge 2, so it's going to go again to the right. So I could draw in that my force here. So on 2 by 3 goes to the right. To the right is positive, so I could key this as being a plus, because again, it's to the right. And so then we can find our net force on charge 2. And so what this would be is this would be the vector sum of these two forces. So this would be the electric force on 2 by 1 plus the electric force on 2 by 3. And what we could do is we could go in and say that that would be, to the right of this magnitude added to one that goes to the right with this other magnitude. And so basically we're going to end up adding the two magnitudes. So this is going to be our plus, what is that? 0.0250 newtons added to plus, and then move that over, 0.225 newtons. And so this 2 goes with that 2, this 5 goes with that 5, and so I get what, 0.25? That's what we get. We got our 3 significant digits. The plus sign here indicates that this would be to the right. Now, since the coordinate system was given in the problem itself, then we can probably answer it as being positive. And we'll code in as like plus our 0.250 newtons would be our good answer. 3 digits, got our units, got the direction. If we pick the coordinate system, then you cannot answer in terms of a coordinate system that we picked. You would have to give like a physical description, like, oh, it's right or left or something like that. Because I don't know if to the right's like east or north or anything at all. So I mean, but since if they gave an illustration, then we could do right or left in the picture that they told us, or since they gave us the coordinate system, we can answer in terms of this coordinate system. But as a general rule, you cannot answer in terms of a coordinate system that you got to pick. So you should keep that in the back of your mind somewhere. How'd we do? Are we good? But again, but if they didn't specify the coordinate system, then we cannot do that. So that's just the deal. Okay.